Hello people, today we're going to talk about topic 2.1 as part of the first video of my hard topic series where we talk about the topics I consider semi-complicated, confusing, or I think a lot of people would benefit from uh, learning more from. And we'll be starting with topic 2.1, aka center of mass. And with it, we'll be talking also a lot about density. Density is one of the key topics, and I believe it's introduced with this not it's not a key topic, it's a key idea, and I believe it's introduced in this topic. Sorry about my cough. I've eaten a lot of cough drops, hasn't helped much though. Okay, so first let's discuss what is center of mass. Center of mass is where the mass of an object is concentrated, and where we like to say its motion is based around. So let's say I have this block. Pretend it's a perfect block, and its center of mass is here. Whenever we talk about the motion of this, we're almost always going to be talking about the motion of its center of mass. And center of mass is going to be based around this center. Motion is going to be based around the center of mass. If I push the block anywhere, or here, or here, we're going to be treating it as a force onto this center of mass. At least for now. In the future, it'll be a bit more complicated, but at the same time, this idea of the force being applied onto the center of mass still applies. I'll discuss that more in later topics. Okay, so let me see if I can just redraw this real quick. Okay, so now, how exactly do we calculate the center of mass? It's actually really simple. The center of mass, or XCM, at least that's my performed way of writing it. You can write other ways too, like this. I just think this looks kind of dumb. So I use this. XCM is equal to M1x1 plus M2x2 plus dot 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 plus MN xn divided by M1 x1 plus M2 x1 or x2 plus dot 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 MN xn. Nope, I messed that up. Whoops, sorry. There should be any m's. There should be any x. It should just all be m's. I messed that up. Whoops. M1 plus M2. Sorry about that. I'm a bit under the weather right now. Hopefully be better in the sooner. Okay, MN. And you could write this as a summation if you want. I'm just not going to. But you can write this as, using the sigma function. And so I'm basically saying we're going to take the x coordinate, or the distance of every single point of mass, add up all those values, multiply it with the mass of the point, add up all of those calculated values, and then divide it by the total mass of the system. So let's say I have a block here, a block here, and a block here. This distance is 2, this distance is 1, and this has a mass of 1, this has a mass of 3, this has a mass of 4. Then I'll just go plug all these values into like this kind of thing. Now, the next important thing to say is exactly how do you find these x values. The x values are actually pretty abstract. We can define this as a coordinate plane, and the coordinate plane can start really anywhere as the origin. It does not matter. It won't change where the center of mass is relative to this. It's easiest if you just say that the origin is like right here to the most leftmost object. You're going to start the leftmost object. That is typically what happens, but you can really establish the origin to be anywhere. And so this block has an x coordinate of 2 because it's 2 away from the origin. This one has one of 3 because it is 2 plus 1 away. So that's those x coordinates. This one will have one of 0. So for the center mass of this system, it would just be 1 times 0 plus 2 times 3 plus 3 times 4 over 1 plus 3 plus 4. And this gives 6. I'll just include the plus 0 plus 12 over 8. And this is 18 over 8. And we could simplify it down to just 9 over 4. So that means its center of mass is going to be at 9 over 4. So that means it's going to be about over here. This is the XCM. Okay, next what we have to talk about is, what if they aren't in a straight line? What if the blocks are instead arranged like one's here, and one is here? Well, in physics, we can typically discuss motion in multiple planes in completely separately. So if I have something and it's traveling like this, we can discuss its motion here, and straight up, and then here straight to the right, as completely separate motions. We can do that the exact same thing with center of mass. You can calculate all the values independently. So first, you can find its center of mass in the x. So you do the exact same thing as we did before. So, we just define here as 0, calculate center of mass here, and let's just say it ends up being exactly in the middle. And now we just have to calculate the center of mass in the y separately. So ignore the fact that they are at different x coordinates. We can calculate their y exactly the same as we would normally. So that means that the y comes out to be like over here. So then this is the exact center mass of the system. We can calculate all this stuff separately. So if we have these two blocks here, and this is their center of mass, along this line here. Actually, it'd be better if I just draw one point. So their center mass is right here. This is the XCM. Moving this block down is only going to move the center mass down too. It's not going to move it any more to the move. It's not going to move any more to the left or right. It's going to stay where it was before. Magic hand move. I don't know what this is supposed to be. But I don't know when I rewrote that. Oh, it's part of my X, maybe. Perhaps, I don't know. Doesn't matter. Okay. Next, we're going to discuss density. Density is how tightly packed the stuff in an object is. Volume is how much space an object takes up. Mass is how much stuff is in it. Density is how tightly packed that stuff is. So, density, which we can represent with many symbols, but the two most common are this. It's called rho, and this. This is lambda. I typically use lambda. And this is equal to mass divided by volume, the average density. That's basically all you really need to know about it. That's really it. Okay, not quite, but that's basically the basics of it. And density doesn't have to be constant, though. If I have this long rod, it can be increasing density as we go along. So sometimes you're going to get equations for what its density looks like. In this case, since we have just a really long rod, what we have is linear density, which is equal to mass divided by the length of the object. And linear density is just the density before a rod, something that's perfectly straight out, typically of negligible width. And the units for all this for density is typically kilograms per meter cubed, while for linear density is kilograms per meter. And now this is going to be important because we're going to spend the rest of our time talking about linear center of mass, the center of mass on a rod. So when we have a free body, it's like a continuous big body, its center of mass can be defined as the integral of x dm over the integral of dm. What does this mean? dm refers to every little bit of mass in the object. So let's say we have this. This could be 1 dm of it, and we're talking about its x coordinate. Or this could be 1 dm, this could be 1 dm, this could be another dm. The mass of that, and this x coordinate is its x. So it's almost the exact same thing as before, but it's just adapted to bodies like this, which are more abstract. And if you couldn't guess, if we add up all those tiny little masses, as we would here for the integral of dm, that just gives you mass. When you adapt this to linear density and linear objects, what we instead get is that dm, because working with dm is very difficult, equals density times dx. And this is going to be the big idea when we're working with these types of questions with linear density. We want to be able to change dm into dx, and that's also the same thing when you're solving for the mass of a free body too. Working with dm is incredibly hard. You want to change dm to a dx. This is how you do it for something that's linear. Okay. Hopefully it wasn't too brief with that. I'm trying to go short on these a tiny bit. Let's move on to example questions. This topic isn't very information heavy. I personally just think that a lot of people find it confusing at first, especially when it comes to working with DM and trying to find the center of mass of free bodies or rods. Let's see here. You have two almost identical blocks of uniform density attached end to end. The only difference is that the block on the right has a density 3 times the one on the left. What is the ratio of the mass to the left of the center of mass of the two block system to the mass of the right of the center of mass of the two block system? So if I were to draw this out, okay. So we have these two blocks, but this one is 3 times as dense as this one. We're trying to find where its center of mass is. So first, I want you guys to try to guess. Which block do you think it is in? That's right. It's going to be in this block because this block is more massive. It's more dense, and because they're the same length and everything, same volume, this one is heavier. Because of that, it's going to lean more towards this one, center mass. And so for this, we could define any point along this as our origin. As I said before, it doesn't matter. I'm just going to set here to be the origin because that's just the most basic thing to do. So 0, and they are of length L. So here, the center of mass of this block, the center of it, because as I'm sure you could guess, the center of mass of a block of uniform density is just going to be at the very center of the block. So here, if you don't know what uniform density means, that means it has a constant density throughout the whole thing. There's no point of a different density than another block. Than another point. Okay, so here's going to be at L over 2. Here's at L. here, the center mass of this block is at L over 3, L over 2. And here's the end at 2L. And this one has 3 times the mass of this one because its density is 3 times as high. And they have the same volume, so using the equation, density equals mass times volume, mass over volume, also meaning that mass is equal to density times volume. So if you triple the density, you triple the mass. Assuming the volume stays the same. So now we can just do this one out pretty easily. So finding the center of mass. It would be L over 2 times m plus 3L over 2 times 3m divided by the total mass of this, which is going to be m plus 3m. And we could just cancel out the m's, and we get 4L over 2 over 4. Did I do that right? Nope, I horribly butchered my math. Sorry about that. I forgot to multiply these things together. That's my bad. Get to 10L over 2 over 4, or 10L over 8, or 5/4 L. So that means the block is going to be, or the center of mass is going to be over here. You have to find the ratios of the masses. I'm just going to write this as ml to mr, mass on the left to mass on the right. Mass on the left is equal to m plus 3m over 4, because we have 1/4 of the block as to the right of it, 1/4 of this big block to the right of the center mass over here, to 3m times 3/4. So this becomes 7 over 4 to 9 over 4, or just 7 to 9 as the final answer. I hope that made sense. Next, you have a rod that is 2 meters long with a linear density represented by P equals 2 plus x, where x is in meters and density is in kilograms per meter. Find the center of mass of the rod. Of course, we're going to go define here as our origin again. And the rod is just going to lie along this, and it's too long. 2 meters long. Its linear density is represented by this. So in order to find the center of mass, you're just going to use the equation. The integral of x dm divided by the integral of dm. And earlier we said that we could say that dm is equal to density. Well, I said p here. I'm just write like this, so I prefer that, times dx. In this case, density equals 2 plus x. So we can say that this is equal to 2. 2 plus x dx. Which means you can turn this top one in, or actually we can just turn the whole equation as a whole right now. xcm is equal to the integral 2x plus x squared dx over the integral of 2 plus x dx. Now, what do you guys think we should do as the limits or the bounds for our integration? What do you guys think about that one? Okay. Well, but, you might be able to guess just based off this graph here. But since we're starting at the origin, so that means we're starting at 0. We're ending at here, 2. Length of 2. 2. 0 to 2. So then you can just do this math out. What we get is x squared plus x cubed over 3 course, here's 0, here's a 2. And this is just doing a basic integral. Here is 2x plus x squared over 2, 0 to 2. You do out this math, and what you end up getting is 4 plus 8 over 3 divided by 4 plus 2, and this gives 20 over 3 over 6, which equals to 20 over 18, or 10 over 9. Okay, now the final example, and this is kind of the example question that I solved where I finally felt confident enough to say understood this topic fully, and that is probably the center of mass of a cone. My idea with physics is that you can typically understand the topic fully by looking at the derivations for each topic and trying to solve it yourself. So that's what I did. I went and figured this one out myself. I do recommend you try to find the center of mass of a cone by yourself too. So, fair warning, I would recommend you try that before you continue watching this video. Now, I will do it right now too. So you're going to do the exact same thing as before, and we're going to start. The XCM is still just equal to the integral of x dm over the integral of dm. But now we have to define dm. When it's on a rod, it's very easily just the mass of each of these little pieces. What about with a cone? The answer is each dm is the mass of each of these little cylinders that we can liken it to. We can liken this cone to be made of a ton of tiny cylinders. And dm is equal to each of these cylinders. So you can turn dm into things. So first you can say that dm is equal to sorry about that, is equal to the density times dv, where dv is each little piece of volume. So we're saying that by multiplying this volume by this density, you get this dm, which I think should probably make sense. Now we have to define what is dv. Well, and get turn dv into equation. We found that dv is equal to this. So what we say is that v is equal to pi r squared h, because we know that each piece of volume is just a little cylinder. And we can swap in some things out actually. For h, it's going to be for each little tiny piece of volume. So for dv, you're going to keep the pi. Actually, you can just take the derivative of this. You get dv dh equals pi r squared. And then just multiply the dh over. But I like to explain it a bit more conceptually. Each little thing here, it's going to be the same exact equation as finding a as finding the volume of a normal cylinder, and it's just going to have the height of dh or dx. I'm going to be using dx to keep consistent with this equation. So pi r squared dx for the h. Now, the last problem we have is the r squared part, because we don't know the radius of this block. We don't want the radius of the big at the bottom, which is what that r is. We want the radius up here. So what you know is that r divided by h, the ratio of the radius to the height of that point is going to be constant. So r divided by h is also equal to little r divided by small h, or x. So at this distance x, this radius divided by this distance x is equal to big radius divided by the height of the total cone. Or little radius, which is the radius we want, is equal to r divided by h times x. And we can plug this little r in for this big r. Don't ask why I wrote like that. I just didn't write it amazingly. Since that dv is equal to pi times r over hx squared dx. Or just dv is equal to pi r squared over h squared times x squared dx. Let me see if I can go quickly downsize this because I kind of wrote this horribly big. Okay, is there a way to make this any smaller? I'm not amazingly good at technology. Okay, you know what? I give up. I'll just write this blank space at the bottom, and if we need to, we'll go back up. So that means that density, or not density, dm is equal to density times pi times r squared over h squared times x squared dx. So then if you plug this back into these equations, what we get is that xcm is equal to the integral of density pi r squared over h squared times x cubed dx, where the integral from times density pi r squared over h squared times x squared dx. And for the bounds integration, it's going to be from 0, because this point's 0, to h, the height of the cone. And we can just cross out all of these because the top and bottom both have them and they're constant values, so we can just take that on the front. That's just a rule of integrals if you didn't know. So we get that the integral from 0 to h of x cubed dx divided by the integral of 0 to h of x squared divided by dx. Just say x squared for the top, that's just the x cubed. So x cubed on top, x squared on bottom. Now, if you were to solve that out, you would get x to the 4 over 4 for 0 to h divided by x cubed over 3 from 0 to h. And we're going to write over here now. That just gives you h to the 4 over 4 divided by h to the 3 over 3. And this gives 3h over 4. So it's the center of mass is going to be 3h over 4 down. So over here. Okay, I hope you have an understanding of center of mass now and also how to solve for it. That's the main thing you have to know, how to solve for it. How to actually apply center of mass isn't going to be a big topic until later. And especially hope you can understand how to do this whole dm thing. Remember, you don't want to have dm still there. You want to swap dm with something else like dv and typically dx. Okay, well, thank you guys for watching. See you guys next time.